Okay, let's unpack this. Today, we're starting a deep dive into, well, one of physics' really deep, persistent mysteries, how the universe actually works at its most fundamental level.
It's a big one. We've been grappling with it for a long time.
Nearly a century, right? Physicists have been wrestling with this core problem in quantum mechanics, and it really highlights a gap in our understanding. So our mission today is to explore this really ambitious theory called Causal Fermion Systems, CFS for short.
hmm
And the claim is it doesn't just aim to solve this quantum puzzle, but maybe even unify quantum mechanics with general relativity.
Which is, the ultimate goal for many physicists.
Exactly. We're going to explore how it tries to knit together the very fabric of reality.
It's definitely a journey that challenges how we usually think about the universe.
It really does. So let's dive into that first puzzle, the measurement problem in quantum mechanics. For anyone listening who's maybe not deep into this specific issue, what exactly is it? Why is it such a stubborn problem?
Okay, so in standard quantum mechanics, the Copenhagen interpretation mostly, we use a wave function. Basically, it describes a system holding all its possible states at once, this superposition idea.
Like being in multiple places or states simultaneously until you look?
Exactly. But then the moment you measure it, something strange happens. The wave function, they say, collapses. It just snaps into one specific state, the state you actually observe.
Okay.
But here's the kicker. This collapse isn't predicted by the main equation of quantum mechanics, the Schrödinger equation. That equation describes smooth, continuous evolution.
Uh-huh.
The collapse is, well, it's an extra rule. It's a postulate that physicists had to kind of tack on.
So it's like the theory describes how things are, but not how we get the specific result when we interact with them. It doesn't explain the transition.
That's a great way to put it. It's an unresolved gap. The theory itself doesn't tell you how or why the measurement makes reality settle on one outcome.
Right, it just says it does, which feels incomplete, fundamentally incomplete.
Precisely. It's been a major headache for understanding how the quantum world connects to our everyday classical experience.
And this is exactly where causal fermion systems enters the picture, proposing what its proponents call a more natural solution. This is where it gets really interesting, I think. How does CFS claim to fix this, to bridge that gap without just adding another rule?
Well, this is the really compelling part about CFS. The claim is that both the wave function collapse and the Born rule.
The Born rule being the thing that tells us the probabilities of getting different measurement results.
Exactly. In CFS, both of those things emerge naturally from the fundamental equations of the theory itself. They aren't added on. It all stems from something called the causal action principle.
Okay, the causal action principle. So that's like the bedrock rule of CFS.
You can think of it that way. It's the core dynamic that governs how these fundamental entities, the fermion systems, interact and evolve over time. And out of that dynamic, collapse and probabilities supposedly just happen.
Wow. Okay, so no external rule needed. It's baked in from the start.
That's the argument. The physics of measurement becomes part of the fundamental physics, not an add-on.
That's elegant, if it holds up. It makes probability not just some weird feature of quantum mechanics, but an actual consequence of the universe's underlying structure.
Right. It suggests probability is inherent, not just a tool we use because we lack information.
Which is a huge philosophical shift, too. But, okay, CFS isn't the only game in town trying to solve this, is it? What about other ideas like continuous spontaneous localization, CSL? How does CFS stack up against models like that?
Good question. Yeah, CSL is another well-known approach. CSL models basically try to modify the standard quantum evolution. They introduce two key things. A stochastic term, which adds a bit of randomness, like a background noise.
Okay, some random jiggling.
Sort of, yeah. And a nonlinear term, which changes the way the wave function evolves, allowing it to localize or collapse over time, even without a measurement.
Right. So how does CFS compare? Does it have similar ingredients?
There are some interesting parallels and some really crucial differences. In CFS, you also get effects that look stochastic or random, but they're not put in by hand. They're supposed to arise from, well, the complex, unknown microscopic structure of space-time itself, modeled as background fluctuations.
So the randomness comes from the environment in a sense, but a very fundamental space-time environment.
Kind of, yeah. And the nonlinearity.
Yeah.
That comes directly from the causal action principle itself. It's intrinsic to the core dynamics.
Okay, so similar concepts, randomness, nonlinearity, but different origins.
Exactly. And this leads to a key difference in the type of collapse model you get. The CFS version is described as non-local in time.
Non-local in time. What does that mean practically?
It's a bit mind-bending. It means the collapse isn't just influenced by things happening right now or the immediate past.
Mm.
It suggests influences could, in principle, stretch across different points in the system's history.
That sounds very different. Does that have implications we could actually test? How do we distinguish these experimentally?
Yes, and this is maybe the most exciting part. It leads to potentially testable predictions. CSL models, for instance, generally predict that this continuous localization process should cause a tiny amount of heating in isolated systems.
Heating, like they game energy out of nowhere.
Essentially, yes, a
Right.
slight violation of energy conservation. And the idea is you might be able to detect this maybe by looking for stray photons emitted from extremely well isolated and cooled systems.
Yeah.
People are designing experiments for this.
Okay, so CSL predicts energy non-conservation. What about CFS?
Well, here's what's fascinating. The preliminary analysis within the CFS framework suggests that it might actually conserve energy.
Oh, so that specific heating signature CSL predicts.
Might not be there for CFS. If those heating experiments find nothing, it wouldn't rule out CFS, while it would potentially cause problems for standard CSL models.
That's a huge potential differentiator, a clean experimental signature possibly.
It's a very important point. It means these incredibly abstract ideas about the nature of reality might have concrete, measurable consequences that let us choose between theories.
Which is exactly what you want in physics. It's not just philosophy, it's testable science.
Yeah.
But CFS has bigger ambitions than just the measurement problem, right?
Yeah.
You mentioned unification. What else does it claim to do or explain?
Absolutely. Fixing measurement is almost like step one. The bigger picture is trying to derive known physics from its principles. Foundationally, CFS shows that Minkowski space, the flat space-time of special relativity, emerges as a stable solution when there are no interactions. It's like the default background state.
Okay, so it gets special relativity right, basically.
Right, but then you start adding perturbations to this background within the CFS framework. Think of these as the fields, particles, gravity, the stuff that makes the universe interesting.
The actual contents of the universe.
Exactly. And when you do that, the claim is that you start to see the familiar laws of physics emerging.
Like what specifically?
Well, you recover electromagnetism described by Maxwell's equations. You get fermions, particles like electrons behaving according to the Dirac equation.
So quantum field theory staples.
Yes. And crucially, when you include gravity in the mix, the interactions are described by the Einstein-Dirac equations.
Whoa, okay. So you're getting general relativity coupled to quantum matter.
That's the result, yes. It shows that in what's called the continuum limit, basically, when you zoom out from the super tiny scale where CFS operates to the larger scales, we usually deal with these established classical and quantum field equations naturally arise.
So let me try and synthesize this. It's not just fixing a quantum issue. It's potentially deriving quantum field theory and general relativity, all from this causal action principle acting on these fermion systems.
That is precisely the grand ambition. It aims to be a unified framework from which all known fundamental physics emerges.
That's aiming for the whole picture, a potential theory of everything, really.
It certainly puts itself forward as a candidate for that, yes. Yeah. A mathematically formulated one.
So, given how huge this is, how radical it sounds compared to standard approaches, what's the reaction been like in the wider physics community? Are people jumping on board, or is it seen as, a bit fringe?
Reactions are mixed, as you'd expect for something this ambitious. You have, say, relativists, people focused mainly on general relativity. They often feel Einstein's equations work incredibly well and might see CFS as, well, interesting, but maybe unnecessarily complex or outside their main line of work. They have a theory that's very successful in its domain.
Understandable. If it ain't broke for their purposes.
Right. But then you have quantum gravity researchers.
Mm-hmm.
These are the people actively trying to reconcile gravity and quantum mechanics. They tend to be, I'd say, more open, more interested in exploring new foundational frameworks like CFS, precisely because it tackles the quantum nature of space-time head-on. They're looking for new ideas.
So the people already trying to bridge that gap are more receptive.
Generally, yes. And the physicists developing CFS, they don't see it as just some mathematical game. They view it very seriously as a candidate for new physics, a mathematically rigorous pathway that could potentially supersede both standard quantum mechanics and classical general relativity.
But it must face hurdles, right? Criticisms.
Oh, absolutely. The mathematical formalism is extremely demanding, very abstract. That's a barrier. And Like many quantum gravity approaches, finding clear, definitive, achievable experimental tests is the major challenge. The scales involved are just so incredibly small.
Right, the energy scales or the length scales are far beyond our current reach for direct probes.
Exactly. So you look for these subtle, indirect effects like the energy conservation point we discussed.
It really highlights the ambition, though. Trying to rebuild physics from such a different foundation, it sounds like it's definitely making waves, even if it's not mainstream yet.
Well, what an incredible journey we've been on today. Seriously. We started wrestling with this century-old headache in quantum mechanics, the measurement problem. How does reality pick one outcome? A really stubborn problem.
And we ended up exploring this potentially unifying theory, causal fermion systems, that might explain everything from particle physics to space-time itself. The idea that all this complexity, randomness, definite outcomes, forces, particles, gravity could all just emerge from one underlying causal principle. That's pretty
It
profound.
really is. I think the key takeaways are that potential for elegant resolution of the measurement problem, through emergence rather than postulates. And the experimental angle, the possibility of energy conservation, distinguishing it from models like CSO.
Yeah.
And of course, the big prize,
Yeah.
deriving known physics, Maxwell, Dirac, Einstein, from this single framework. It offers a coherent mathematical picture.
It really ties things together, or aims to. So here's something to think about for everyone listening. This whole discussion raises a really fascinating question, doesn't it? If fundamental physical laws, things we thought were bedrock rules, can actually emerge naturally from a deeper, simpler principle like this causal action, well, what else might work like that? What other phenomena in the universe, things that seem totally disconnected now, might actually be linked by some underlying structure, some deeper set of rules we just haven't grasped yet? What else is waiting to emerge? Makes you wonder, right?